Welcome back to Accelerated Math 2. Today we're going to take a look at geometric sequences in series, and perhaps the best way to start this off is to actually take a look at a geometric sequence. So the following sequence of numbers, if we start with 2, 6, 18, if you were to make a prediction about the next term of this sequence, hopefully you've identified that to get from one term to the other, we're multiplying by 3. And so the next term would be 54. And this right here is an example of a geometric sequence. A geometric sequence is characterized by a common ratio. That is to say that the ratio between adjacent terms, so the next term divided by the current term, is always equal to a fixed ratio, and in our case, that fixed ratio is 3. Another way of thinking about a geometric sequence is to say, to get from one term to the other, we multiply by that common ratio r. And so what we'll try and do now is derive the general rule for the nth term of a geometric sequence. Just like with an arithmetic sequence, there are two key parameters, and as long as we know these two key parameters, we're able to work out any single term in the sequence. Those two key parameters are the first term and the common ratio. Every single term can be expressed as a function of those two things. Clearly, the first term is just the first term. To get to the second term, we take the first term and we multiply it by the common ratio. To get to the third term, if we start at the first term, we actually multiply by the common ratio twice. So it's A1 times R, which is really R squared. To get to the 50th term, we have to start at the first term and multiply by the common ratio 49 times. And in general, if we wanted to get to the nth term, an, we'd start at the first term and we'd multiply by the common ratio n minus 1. And that right there is our explicit rule for a geometric sequence. So let me give you a moment now to have a quick practice and try the first example. Hopefully, checking over your answers, you've managed to obtain the same results as me. Before you have a go at this next example, please remember that the two most important things for a geometric sequence are the first term and the common ratio. If you can express the given information in terms of those two key parameters, you'll have no problem solving this next one. So hopefully what you did is you established that the first term times the common ratio is a way of expressing a 2. And you also managed to gather information in terms of A1 and R to express the fifth term. And then you went ahead and you solved that system of equations, and you should have established that the value of R was 3 over 2. And coming down, you should have established that the first term was, in fact, 4. And then we know that the 8th term is really just the first term times R to the power of 7. And so we just go ahead and we substitute that information in. Clearly, there are other ways of approaching this problem, but I think the broadest approach is to represent the information that's given in terms of the first term and the common ratio, and then solve the system. If you follow that instinct, you'll have no issues handling anything that you see up on the upcoming assessments. So as was the case with the arithmetic series, we can also find the sum of a geometric series, and that's really just when the individual terms of a geometric sequence are added together. There's a formal proof here, and it goes into it in a little bit more detail on page 683 of your textbook, but I do want to make sure that I draw your attention to this. Let's take a look at how that formula is put into action with this next example. I'm going to pause right here and give you a moment to have a go. So to find the sum of the first 8 terms of this geometric sequence, or series, we are going to go ahead and use the following formula that we just derived on the previous page. We can see pretty clearly that there are 8 terms because we've been asked for the 8th partial sum. We can see clearly that the first term is 4. Perhaps not so clear to see is what the common ratio is. So we have a little bit of work to do just here in order to establish that it's 10 over 3. Once we know that, it's simply a case of putting the information into our calculator and rounding our answer to 3 decimal places. This next example is one that I really want to make sure that we work through together. The first thing that we need to appreciate is that when we see this dot, dot, dot here, What it really means is that this series is infinite, right? It does not stop. It continues on. It's got an infinite number of terms. And so at first, you might think to yourself, how on earth can I find the sum of an infinite set of numbers? Let's first of all have a look and see what the common ratio is. We establish the common ratio. We know that it's really A2 over A1, or we could use A3 over A2, etc., etc. We have a look there, 1 over 5, or we could have done 0.2 over 1, but they're both the same, and so we have, in a way, just confirmed that this series is geometric, and we've also established that the value of the common ratio is really 1/5. Now, it might seem ridiculous to go ahead and try and find an infinite sum, but let's just remind ourselves of the formula. So the sum of the first n terms of a geometric series is always the first term times 1 minus the common ratio to the power of n, all divided by 1 minus r. And in this case here, we have n equal to infinity. We know that the common ratio is 1/5. We also know that the first term is equal to 5. So it appears that we have all of the necessary information, but we might be a little bit concerned about the fact that we've got this n equals infinity. Let's just see how this pans out. So the infinite sum should be equal to 5 multiplied by 1 minus 1/5 to the power of infinity, all over 1 minus 1/5. Well, actually, when we go ahead and we try and establish and put this into our calculator, we're going to run into a problem because we cannot go ahead and put 1/5 to the power of infinity in. However, if you imagine taking 1/5 and multiplying it by 1/5, 1/5, 1/5, and 1/5 again and again and again, what do you anticipate happening to that result? Well, let's just take a look. If you had 1 over 5 raised to the power of infinity, that's really 1 to the power of infinity over 5 to the power of infinity. 1 to the power of infinity, well, 1 to the power of anything is just 1. So we've really got 1 divided by 5 to the power of infinity. And actually, that value there tends towards 0. So what we can say is that this is so infinitesimally small that we're going to approximate it to 0. And what we end up having is that the sum to infinity is really just 5 over 1 minus 1/5. And in this case here, that value is 5 divided by 4 over 5, and that's really 25 over 4. So bizarrely, this infinite sum actually has a finite value. And if you think about it, the terms of this sequence are getting progressively smaller and smaller and smaller and smaller. So we get to the point where we're effectively adding nothing. We're adding 0 every single time. And so we've converged on this finite value. Now, perhaps an important question to ask is under what conditions does this hold true? And really the key is the fact that this r to the power of infinity became 0. And if you check in your notes, when is that going to be true? Well, it's if the absolute value of the common ratio is less than 1. Any value between -1 and 1, if you raise it to the power of infinity, it's going to tend towards 0. It's going to get ridiculously small. Now, I realize that many of you have already worked with things like compound interest, so let me give you a moment to have a go and approach this next application problem from the perspective of geometric series. So a couple of additional notes here just to help you out. We need to really consider each of these 48 deposits separately. So for example, the $70 that he deposits on that first month, it's going to collect interest, and that interest is 2% per annum, but it's compounded monthly. So he's going to actually collect interest 48 times across the course of this 4-year investment. The following month, he's going to invest another $70, And again, that's going to collect interest, but it's only going to collect interest over a time frame of 47 months, and so on and so forth, until he makes that last payment of $70, and that's going to collect interest for only 1 month. So we need to consider how many terms are there in this particular series. We can see that by analysing the exponents, if we're going from 48 through to 1, we know that we've got 48 separate deposits. So we're really trying to find the sum of 48 terms. For me, I'm going to rewrite this statement, but I'm going to write it backwards. So I'm going to allow my first term to actually be that last deposit. And for me, that's just going to help to make life a little bit more straightforward in terms of establishing what my common ratio would be. The last term is going to be that first initial payment, so 70 times 1 plus 0.02 over 12 raised to the power of 48. This helps me to see that this really is a 1, and my common ratio is simply that interest that I'm gaining each month, and then the number of terms that I have is 48, and so I can go ahead and say the sum of the first 48 terms really should be A1 into 1 minus r to the n, all over 1 minus r, and actually that value for n is really 48, and the value for r is this common ratio here. Take a moment now to go ahead and work that out on your calculator, and we'll compare and see if we've got the same result. So hopefully you were able to put all of that necessary information into the calculator. It looks a little bit of a mess, but you should really have a value 3,500.852, and really, since we're talking about cash, we need to give some units, and it's perfectly okay to round to 2 decimal places. Having a look at the next example, we've got to go ahead and find the first term of the sequence that's given here that exceeds 4,800. You're welcome to go ahead and use your calculator in this case. Let me give you a moment to have a go, and then we'll check back in together. So the first thing we need to do is actually check what type of sequence this is. You might just be able to eyeball it and determine that it's geometric, because you can see the common ratio is √3. If not, do a quick analysis for yourself. But once you've established that it's a geometric sequence, you can go ahead and derive the explicit rule for the geometric sequence. And then it's really a case of choosing one of two approaches. You can either approach it graphically and draw a graph of AN versus N, and then see when does this graph exceed 4,800. Or you can go about it algebraically and use logarithms. And I've used log base 10 simply because log base 10 is what you'll have access to when you're in test mode. Once we've established that n is equal to 13.907, we must remember that n represents our position in the sequence, and so it must be an integer value. And so the first term that's going to be greater than 4,800 is actually the 14th term. As far as your assignment goes, there are a couple of extra challenge problems in the note set. Please make sure that you go ahead and finish those. And then the assignment from the textbook is listed here and at the bottom of your note sheet as well.